Okay, now welcome. Welcome everyone. We are back to another Friday quantum hardware course. Uh, Today I'm planning to talk a little bit about beam splitters. In the last lecture we talked about phase shifters, I think, quantum properties of phase shifters. And today let's see the beam splitters. So I'll start sharing. Okay, so again, just some brief introduction with the slides, and then we go to the whiteboard. So this is another section onto hardware course, optical models. So it's just introduction again. So in the last lecture, just to remind you, we discussed the most experimental accessible devices for manipulating photon states using optical instruments are mirrors, phase shifters, beam splitters, among others. Today we'll focus about beam splitters, quantum properties of beam splitters. So compared with other fundamental experiments in physics, like optical tests of quantum mechanics are often distinguished by their simplicity, because most of the quantum optical experiments do not require like a big industry, right? Some few people and a tabletop experiment, and you can do a lot of things. And a simple optical beam splitter is a device that demonstrates the quantum nature of light. And quite several puzzling quantum effects have been seen by splitting or recombining photons at small cube of gas, for instance. Like a lot of experiments, some of them that we will discuss, especially in the quantum T, we use a lot beam splitters. And for instance, like in the Mass-Zehnder interferometer, we use beam splitters to formulate the puzzlings, quantum puzzlings that appears there. And additionally, the beam splitters serve as a theoretical paradigm to other linear optical devices. For instance, like interferometers, semi-transparent mirrors, dielectric interfaces, and so on. So, ideal beam splitter is a reversible, lossless device in which two incident beams may interfere to produce two outgoing beams. And these outgoing beams has a fraction of refraction that they call R, reflected, sorry, that they call R, and an incident light that transmitted part that they call T, which is and the total is T plus R is equal to 1. They are partially silvered pieces of glass that split a light beam into two. This situation may be reversed by sending the two beams back to the glass, where they interfere constructively to restore the original beam. And however, if we change the phase of the two beams, the mutual interference generates two outgoing beams in general. So four beams might be involved in a simple beam splitter experiment. So two incident and two outgoing light modes that can be represented in this case in figure 7.3, that is in the Nielsen-Schwann book. In this example here, they are using beam splitters of this type, 50-50 beam splitter, where the theta is the angle related to the refractive and transmittive index. So in this case, theta is pi over 4. So okay, let's see some of these things now in the whiteboard, right? So just introduction. Okay. So the first the first question that we could formulate is, just put here bean splitters. So the first question is, what happens if two coherent side beams with complex amplitudes, let's call A in for the ingoing beam and B in for the other ingoing. So what happens if they interfere? Well, we have this answer for classical optics. We know this well. So let's put this in classical optics. The amplitudes are simple, superimposed according to the linear transformation. Let's just remind here that A out would be the amplitude associated to the outgoing beam, what to in B out for the other outgoing beam. It's B would be my operator. Okay. That's a matrix that we see. A in, B in. Operator in the quantum case, right? We are still in the classical case. So B here is just a matrix. So in the picture we have, I think that the picture is here. Okay, in this picture here, but this is the B. Put here bigger. This is what I'm calling B in. And this is A in. And this would be like B out. A out. Okay. And here is the transformation that I'm calling B cap B. Okay, so this B cap B is described by the matrix. B would be something like, let's call B00, B01, B10, and B11. Okay. So in these amplitudes, remember the amplitudes is associated with the electric field, just to remember here. E is proportional to the amplitude of some wave, electrical wave. E, KR, omega t, for instance. So in A or B, in and out, are proportional to electric fields. Okay. So these amplitudes is classically is the classical electric field associated with the light that is coming, the ingoing light. So okay, and in the quantum description, I will show here this a thing like this in general, like classically, this B here, this cap B is associated with a transmittive and reflective index, which is something like this. We will see, like quantically, we want something similar to that. Something. The position here of T and R is it like a choice? Don't need to be in this diagonal here. The principal diagonal T could be R here, okay, and T could be here. In different references, we'll see different R or T in different places here. And this minus sign here is also sometimes is in this term, sometimes in this other. This is in general is a convention. But the thing is, this an expression like this is confirmed experimentally. Okay, so let's call this B classic. So this is phenomenologically confirmed. Okay, and to have like a quantum description, we want like something similar with this, and we can do like, since we know this formulation, this result, basically, we could like have a direct, let's say, demonstration that using like quantum optics, we could like found something similar to this. So let's put this way. In quantum optics, the complex amplitudes A in B in corresponds to the annihilation operators. It's the same way we did when we quantize the electric field, remember? So of the incident fields. field. So quantizing the electric field, it's proportional to the amplitude, like A in. Okay. And evidently the outgoing beams will be quantized as well. Outgoing beams are characterized by the operators. So A, out, and B. And the linear relation that we saw above, we assume that it's still valid. We assume that the linear relation given above is also valid. To the quantum physics. So A, B, out is the matrix B, A in, and B in. Okay, so in this model, and B here now is an operator, right? So in this model, we can describe most of passive and lossless devices in which two beams interfere to produce outgoing fields. It's okay. So let's see some important properties that in the Nielsen-Schwenk book he just mentioned, but he didn't prove. So that's why I start indifferent from them. So let's determine some properties of the beam splitter. Okay. So consider light beams, in fact, incoming light beams consider incoming light beams and outgoing beams. Consider that, sorry about that, that incoming light beams and outgoing beams are both independent bosonic modes. Bosonic because we are talking about like photons, right? Bosonic modes. So we already know the relation about the annihilation and creation operators. We already know the following relation. So I'll put here A out, A dagger out, it's the same A in, A dagger in, the same for B out, B dagger out, and B in, B dagger. This is equal to 1. We saw like in the when we were quantizing like the harmonic oscillators. And the same for when I have the annihilation with annihilation of the old mode. Because they are different modes, so they are independent, right? So A out, A in, B in. This is 0. So we can see some important properties I forgot to put here. B, again, I will call B. In principle, is a matrix like this. This is the elements, B 0, 0, 0, 1, 1, 0, 1, 1. This is the matrix. And this is the components. So we can see some interesting relation about them using these properties. For instance, we could like use this first here. So A out, A dagger out, describing this matrix here. Let's return Okay, so with this matrix here, we could like evaluate A out in terms of A in B in, and B out in terms of A in and B in using this. If you do that, if we do that, we'll found A out will be just A in, B, the component B00 plus B in B01. And A dagger out will be A in. Dagger will be this is B00 complex conjugate plus B in dagger B0 conjugate. This is equal to 1. So, okay, so we could like develop this. We will find like A in B00, A in dagger B00, potato, plus A in B00, B in dagger B01. Okay, and the other term, this with this and this with this. So plus B in B01, A dagger in B00, and the last is this last two. Commutator of B in B01, B in dagger B01. This equal to 1. Okay, but because this, like the cap B's are just numbers, just components, so they can go outside the commutator. So this will give me like B00 and the commutator A in, A dagger in. That we already know that this is 1, right? Plus the same here, this component B00, B01 conjugate, A in, B in dagger. They are independent, so this is 0. Plus B01, B00 conjugate, B in, A in, dagger. This as well, they are independent. Independent means that we can like measure both with high precision, right? When the commutator is 0. And this is B01 square, B in, dagger. This is 1. And all these things are equal to 1. So, very nice properties is that B00 square plus B01 square is equal to 1. And we could do the same for B out, B dagger. We will find B10 square plus B11 square equal to 1. It follow the same procedure we did here. Okay. And we could also use the independence of the light beams, and we could find as well A out, B out dagger, and using the same procedure. This, remember, this is 0 initially, okay? And when we develop this, like we did here in this first case, we would find that B00, B10 conjugate plus B01, B11 conjugate is equal to 0. These are 0 because they are independent. So if you use these properties here, like this one, this one, this property is this and this is the same as saying that the B, let's say in other words, B is unitary. Okay, I'll leave you guys, you can prove this using these properties, but it's a long and boring calculation. I'll leave you guys like to do. You just use these things we will find here. We could find B is unitary. It means that B dagger is the inverse of B. Okay, and this is homework. Like it's easy calculation, but it's tiresome. So we have another very nice things to discuss. Okay. So apart from the unitarity, the beam splitter coefficients are free parameters that depend on the particular experimental situation. For our purpose and applications, we are interested on, let's say, real, the components are real, right? And rotations, matrices. So in this case, we could represent B in terms of the, like we did in the classical case, in the transmissivity T and the reflectivity. Yes. So B, we could again use like this formation, but the sign here in the position of T and R are just like convention, right? We confide in different references, different positions like T and R. And because they are unitary, so B dagger B dagger should be the inverse of B. The inverse of this is just this T minus R. Okay, and the relation T squared plus R squared equal to 1. These I'll leave as homework too. We use that the same properties we saw. If you use like instead of B00, B10 that we did in previously, so if you use T and R, you can find like relations like this. Use this matrix. So this is homework. And these accounts, because I have like the total field, like this, this means that we didn't lose any information. Like the reflective and transmittive index are equal to 1. So this accounts for energy conservation. And this relation, that is homework, accounts for energy conservation of lossless, idealized lossless ports. And we could like choose like T and R. We have a lot of options to choose like T and R that satisfy these conditions. But we choose like the simplest here. So the simplest choice to satisfies these conditions is like we could choose T or cosine of theta and R equal to sine of theta. Okay, look, we could as well choose put a phase here, difference of phase E, I phi. And this phi would be a phase difference between the transmittive and reflective index. But we can consider like this phi, like in multiples of pi, for instance. So this would be like 1 in general. Okay, so if we put this exponential of I here, these things would be satisfied. So, okay, So okay, with this choice, we can like find change the color. Then in B, this guy here will be just a cosine of theta, sine of theta minus sine of theta, cosine of theta. And B dagger, this cosine minus sine, sine, cosine. So we would have just to be in accordance with Nielsen-Schwenk, A out, B out is this cap B. That's cosine, sine minus sine, cosine. A in B. And so we have A out, A in cosine of theta plus B in sine theta. And B out is minus A in sine theta plus B in cosine theta. And these are the equations 7, 6, 7, 16, 6, 17, and 7, 18. The Nielsen-Schwenk. And in the picture, they put like the picture we show. They have presented beam splits in this way, like the A, this is B in, A in. They call like the out here is B minus A per root of 2 in, right? And plus B in per root. This is the out. And this is why they choose like theta equal to pi over 4. Okay. And then
there's a question in the chat.
Oh, okay.
Constantine, can it be done in reverse? Sine t equals sine t, r equals cosine theta.
T equal?
I think lower capital T equals sine theta, capital R equals cosine theta.
Yeah, it could. I mean, this is the like just a choice. Yeah, the choice this way. But you can find different references, the T like sine and R cosine. It's outside the same condition. And this result would be like the same as well. Just change here. At least for this specific case, right? I don't know if to have 50-50 because this will not change. I don't know in general. But I saw in different because this the Nielsen-Schwenk here, they start here, right? I just give some introduction before, and they start here. But I don't know. I saw in different like references, they choose like T and R differently, like change it cosine and sine. So yes,
Might be just considered different coordinates.
maybe, yeah. What you define like, because you could have like, I think this picture is much simple. Like we have incident and reflective here, transmitted and reflected, right? And depending if we choose these coordinates here, this would be like the incident, the in. This is the reflected. This is transmitted. Okay, so yeah, we have this, and for B dagger is the same. The only difference is plus here and minus here. So this is the B and the B dagger, like in the Nielsen Schweinberg picture. They represent this point. This dot here is just like to say that this is the beam splitter, and this is the conjugate, right? The dagger. And here, yeah, this is plus, and this is minus. B and A. Okay. So okay, this is one way to describe, but we can like do the like the Nielsen shrink did, and we find the same result using like a Hamiltonian formulation. So we confine the same result using the following Hamiltonian. So for a beam splitter, and this is also like your option. And the problem here is that the Nielsen Schwank did make some confusion, and I show you guys we need like to fix in the book. Okay. So H for beam splitter, he defined initially in this way: I theta A B dagger minus A dagger B. Okay, and he defines the operator, beam splitter operator. And the beam splitter performs the unitary operation. So again, I'll call B will be just like the exponential of H. In this case, we have don't have this. In this case, E is just theta AB dagger minus A dagger. Okay. Okay, and we want to see this, how it relates with the dual rail representation, right? For the quantum computation. So, but to see, it's important to see some transformation. So the transformations affected by B on A and small b which will be later useful. So we see some relation here that will be useful when we applied for in the dual rail representation. Okay. So the relation are B, A, B dagger. We find that this is A, sin of theta, plus B, sine theta, and B, B, B dagger is minus A sine theta plus B sine theta. That's the thing that we found, but now we use this, that will be useful. So to verify this is simple. To verify this, these relations. To verify these relations, we use the Baker, Campbell, Hausdorff formula. Okay, he used like a very interesting form that is present in exercise in capture 4. So it's exercise 449. They prove this. Exponential was lambda g, a exponential operator is the sum 0 to infinity lambda to the n cn. So this I will leave as homework as well, okay? Because it's homework. Just to prove this. But this is the Baker-Campbell-Hausdorff formula that he expressed in this way, defining the coefficient C in that way here. So just to define things, lambda would be a complex number, and A, G, and Cn are operators. And Cn is defined recursively. As like a sequence of commutators. So C is 0. This is equation 727. So C0 equal to A. This A here, okay. C1 is just the commutator of G, and C0, in this case, is A. C0. C2 is the commutator of G and C1, and you see that we are having like the usual Baker-Campbell-Hausdorff formula. C3 is GC2, and so on. Cn is G Cn minus 1. Okay, so we could like use this formula to found the relations that we said above. Just like copy above. But here has a detail that I'll show now, guys. It has a like in the book, it has a mistake here. So let's put here since we already proved that like A dagger is equal to 1. It's the same for B dagger. Right? This is B. B dagger and A dagger. So in the book, has this errata here. Nielsen Schromm. This is in the definition of G. G is defined this way. This is the correct way, because in this way it is consistent with the definition of the Hamiltonian. Let me show you guys here. In the book. Okay, here in the book, we define variables. Not fine here now. Oh, here. G. Oh, this is right. So no, it's different, right? Here is the minus sign is opposite. I define A B dagger minus A dagger B. Here you define the minus different. No, so here is fine. That is this one. It's okay. But it has this erratum here. Let's see here. Yeah. This is the like official output. This is the Nielsen, Michael Nielsen web page. I'll put here for you guys to check. Okay. At the bottom of page 291, G is defined incorrectly. It should be A B dagger minus A dagger B. Yes. To be consistent with 7.24. Let's see. So it defined A dagger B 7.24. To be consistent with this. So this A B dagger minus A dagger B. He defined here A dagger B minus A B dagger. Okay. So because of this, all these results here, and just definition, you could define this way, you have no problem, so, but just the sign would be different. But to be consistent with the definition of the Hamiltonian, he make this confusion. And we are fixing here. So the result is not this. That is here. The result is in the erratum. Is this. So we have a plus here in the sign. Okay. So I'll follow the erratum. Okay, let's return. So I'll follow the calculations that is in the link I just sent to you. Now I had a problem here. Can you guys hear me?
Yes, I hear you fine.
Yeah, I have some problem in the computer. You know? It's not obeying me. Yeah, technical problems. Let's see here. Oh, I see. That is not working. Yeah, I don't know what to do now. Okay. What's happened? Okay. Goes. Let's open again. Okay. Okay, we're back. Good. So I will follow this, okay, this definition. It's not the other is wrong. You could like define different sign, but you'd have problem because you define the Hamiltonian one way and the G another way. This G will appear here in the Baker-Hausdorff formula. That's the definition of B, the cap B. So if we define G this way, so we could like show that GA, I'll make just the first, okay? And you guys do the others. So A, B dagger minus A dagger B, A. This A, B dagger A minus A dagger B, A. And this is just A, B dagger A, the commutator. This commutator is 0 because they are independent. Plus A, B dagger, which is 0 because A commutes with A. Plus the other term, minus in this case. Minus this case, this first A dagger A minus A dagger A B. And A dagger A is minus 1. So this is just B minus, no, plus B, because it's minus 1 and minus. Okay, and the same, we could see the same for G and B. The commutator will be minus A. And if you use like this, and this relation, and those relations here, but these relations here are called 1, these are called 2, and these are called 3. If you use this, all these things we could see like that C Cn, when n is even, this is equal to I n A, and Cn when n is odd, this is minus I n plus 1 B. Okay. To see this, you just need to use use equations. These equations that I call here 1, 2. 2 is this, and 3 is this. 3. Okay, you can see that this is in general. We did just these two, but you can, like, because it's a recursive formula, we will always like use these results, and we will always find this. That is the formula that is in the erratum, no? The link I sent. So I don't want to show now because I'm afraid to have problems again. And so if you use these things like B, A, B dagger will be a sum. Yeah, because we are B, A, B dagger is exponential of theta A, B dagger minus A dagger B. And these I'm calling G, right? That's the definition. A, cap A, exponential minus theta A B dagger minus A dagger B. This is G. Okay. This is exponential of theta G, A exponential of theta G. This is B, right? Sometimes my J and B don't get confused. This is B and this is G. Theta G. Okay, so if you using the Baker-Campbell-Hausdorff formula, in the form of equation 727, like B, A, B dagger, it's this expression here, exponential of theta G, A exponential minus here, minus theta G, that's the formula. N and factorial Cn. And use this, right? In general, we have this. So putting these things here, we will find that B, A, B dagger, will give this sequence N even, and even I theta N and factorial A minus the sum and odd I here, sorry. I theta N and factorial B. Okay, this part. This is the odd part, and this is the even part. So if you expand this sum, this will give A 1 minus theta square over 2 factorial plus theta to the 4 over 4 factorial plus other terms minus B. So I theta, it's I here, I theta minus I theta to the cube 3 factorial plus I theta to the 5th 5 factorial plus other terms. And this will be just the sequence for a cosine. And this, when we multiply this I here with this I outside, this will be the sequence for the sine. And so we could like prove the expression, right? So use the fact that cosine of x is the sum n to the 0 to infinity minus 1 to the n x to 2n to n factorial. That's 1 minus x squared 2 factorial plus x to the 4 factorial. That's this case. And the same for the sine. And sine of x and 0 to infinity minus n to the n x to n plus 1 over 2n plus 1 factorial. This is x minus x to the cube plus x to the 5. That's this guy here when we multiply these i's, give this result. So b a b dagger, the expression a cosine of theta plus b sine of theta. And this sign is different from the Nielsen-Schwenk book because the definition of the G, right? So you guys can check. But it's in according with the link. So, okay, and we could check as well that, so we calculate this. We calculate this. And you guys could check that b dagger using the same procedure will give b cosine of theta minus I sine of theta. Okay. Follow the same calculation, the same sequence. So this is normal. Okay, but now doing a little bit of quantum computation, and we finish. So we could, like, in terms of quantum logic gates, B performs a useful operation. Let's see here. B, when applied to the state of 0, modes, vacuum state, this is exponential of theta a dagger b minus a b dagger applied to this state. And to get this simple, let's define this a g applied to 0, 0. Okay. So expanding this is the thing that we are used to do. Just need to expand this exponential operator like g plus theta g squared over 2 factorial plus theta g to the cube and so on, applied to 0, 0. So g applied to 0, 0, you'll see that it do nothing, right? A plus, so use the definition of g, a plus b minus a b 0, 0. So here, just to don't get confused, in this notation here, like A is applying to this, A is applied to this. In B, let's change the color, B applied to the, okay? So this will give, like, let's do detail the first, A, B dagger. So this 0, 0 state here is the same as 0. This is the state, let's say A, 0 in the state B. Okay. So A plus applied to this state will give 1, it create 1 photon. So this will give me like 1 scalar product of 0, right? Because B is this annihilation operator in the B state. So this is 0. So it's 1 times 0, which is 0. Minus A applied to this is 0, so doesn't matter. Times 1 plus B. So this is 0. So in the same will be when we have like G squared, because G squared will apply twice this and we have 0 again. So B, cap B, applied to this vacuum state. This will give like this expression here will be 1 plus 0 plus 0 and so on. 0, 0. So we do nothing. 0, 0. Okay. So this means that no photons means that when no photons need the input mode exists, no photons will exist in the output mode. Okay, so we could see what happened, but I think it's, let's just see this and we finish, and then we finish in the next class, next lecture. So just to finish for today, let's see. Let's see what happens if one single photon exists. Like, for instance, for instance, node A. So you just need to remember that one photon state is the same as A dagger 0. So B01, make some confusion here. Let's see. Yeah, sorry, I make some confusion here. A, but it will not change this thing here. Okay, but because let's see the definition B, this B0, so I'm calling this B and this one, and I think I did the opposite here, but do not change because both have 0. Yeah, I think I did the opposite here. Sorry. So this is the green and this is the red. And so this is the convention we are using, that Nielsen Schwann book is using, is this one. Okay? The B is in the left mode and the A in the right mode. But here it makes no difference because this would be the opposite, but it's 0 anyway. But in this definition, it changed. So, okay, so this is B. 0, I'll put B here, don't get confused. A dagger 0. So this B01 is the same as B. A dagger and 00 will return to this 00. Okay? So B01 would be written this way. And remember that this A dagger applied to this to the right mode only. Okay, but you could use here the fact that a B is unitary. But B dagger is equal to 1. So if you do that, we could write this B01 is the same as B, A dagger, B dagger 00. And we know that we already proved that this guy doesn't change. When B is applied to 00, this is just 00. So this is the same as B, A dagger, B, 00. And from equation 733, we could find that 733 is this equation. B, A dagger B, dagger is equal to cos A cosine of theta plus B sine of theta. And B. No, sorry. 733 is this. And we could prove that B a dagger is just a dagger cosine of theta plus B dagger sine of theta. This is just the again we just use like the Campbell-Hausdorff formula to prove this and do the same thing that we did before. So this we could check like in our homework. Well, so using this formula here, we could find the B01 is this guy, B a dagger B00, which is a dagger cosine of theta plus B dagger sine of theta 00. So, okay, so this is just a dagger 00 cosine plus B dagger 00 sine. And this guy, sorry?
There's a question from Bob. Should B ket 00 have a dagger?
B
Yeah, I'm looking at the equation. It's 1, 2, 3, 4 lines up from the bottom of your white, or
4 lines.
or 5 lines, excuse me. Look at the right side of the equal sign there. You have B, A dagger, B, ket 00. Shouldn't that be B, A dagger, B dagger?
Oh, yeah, here, yeah.
Okay.
Oh, here is, yeah. Okay, here, right?
Yep.
This is 0, this is dagger.
Right.
And so this is dagger too, because this is the continuation.
Yep.
Okay, and I use this. I use this formula. No.
Good catch, Bob.
And so again, A dagger applied to the right and B applied to the left mode. So this will give us 0, 1 cosine of theta plus 1, 0 sine of theta. B0 is this. And we could do the same. So this is important. We could do the same for B10. So it's the same procedure. You do the same thing. We'll find 1, 0 cosine of theta minus 0, 1 sine of theta. Okay. Remember that in the dual Breuer representation, we have these guys, and we represent these guys as our logical qubits. So this the logical 0 and 1 manifold states, we have, this is homework, okay? You guys have a lot of homework today, but it's the same calculation. This is the logical one. I think we define a couple of lectures before, and this is the logical zero. And in this representation, we could find, like, since B 0, so 0, 1, that this guy here is the B on zero logic, this is cosine of theta, zero logic, plus sine of theta, and 1 logic. Okay, that's this expression. And the other is B 1, 0, that is, and use this formulation. This is the same of B 1 logic, cosine of theta, 1 logic, minus sine of theta, 0 logic. And we could, like, find the representation in the matrix representation. Matrix representation for B in these logic gates now. Like B, if you use this, like the 0, 0 term, 0, 0, if you apply 0 here, the bra 0 in the left, in this first term, this will be this term here, 0, 0 in the matrix, and this will be cosine of theta plus 0, because the 0, 1 is 0. And the 1, 1 is this term here, will have cosine of theta as well. Okay. And the 0, 1 is this, right? 0, 1 will apply the bra of 0 here in the left, so only this term will survive. Minus sin of theta. And this term is 1, 0, so the bra here in the left, only this will survive. Sine of theta. This is equation 735. Okay? And this, you could relate this with a rotation. Note that we could write (735) with like this. 735, that's B, with this term. Exponential I theta y, where y is the Pauli matrix, minus I 0. This is the matrix representation for this guy. You can see this directly. I mean, we just expanding the exponential, you see that you could write in terms of matrix. You could find something like this, but you could, like, use directly the formula using formula 2.58. the Nielsen-Schwenk book, okay? This formula is this exponential I theta V scalar sigma is just cosine of theta. This is the density matrix plus I sine of theta V scalar sigma. Sigma is one of the Pauli matrices. So you can use this formula, the exponential of minus I theta y is exactly what we have. Cosine of theta minus sine of theta, sine of theta, and cosine. Okay. So, but here it has another in the, I think in the Nielsen-Schwenk book, it's not in the Hatton. They put here positive. But I think this is wrong. You guys could check this. But I check, and to have this form here, it must be negative here. But I think it's in the Nielsen-Schwenk we put this. Okay, I think this is wrong. This is not this. This will be the minus here. But I mean, in the end, there's not a big deal. But this is not in the Hatton. They are not say that this should be negative. But okay, so just to finish, like phase shifters that we saw in the last lecture, and beam splitters that we saw today together. Hello, arbitrary, single qubit operations. To be performed to optical qubit. Okay, and you could say like as you saw in the last lecture, P, the operator related to the beam splitters, is related to a rotation in the z direction. We write this way. And the beam splitters is related to a rotation in the y direction. It's minus over 2. So let's say performs RZ rotation. And the B splitters performs RY rotation. Okay. So okay, I think today is almost 5 o'clock here. So a lot of things. The only difference that I found is different from even in the Hatton was this. It didn't fix this in the Hatton, but in the book, if you guys book. In the book, it says like the positive here, you see. But I mean, I check here. You guys could check this as well. Maybe I make a mistake, but if it's positive, the sign is positive, so the minus should be here, and this should be positive and negative here. In Yehatun, it doesn't fix this, so I think it's another mistake here. But okay, it's not a big problem. So okay, so I'll stop the recording because otherwise it would be too long video. But you guys can make questions if you wish.
Thank you, Carlos.